Sensations. The raw data we encode from our physical environment are just a random mix sights and sounds, tastes and smells. They provide little meaning in and of themselves.
Say, who's that beside you there, Jen?
Roy, with an R.
How do you spell that?
You tell him.
R-O-Y.
R-O-Y?
Yes.
To construct the outside world inside our heads requires us to select, organize, and interpret these sensations, transforming them into perceptions that create meaning.
Oh, watch out. What's this here? Whoa. Hey, what is that inside your head anyway?
What you become aware of can be quite different from what your visual system processes. So that's where our intuitions go awry. We assume that everything that strikes our eyes is something that we consciously see, as opposed to just process in some way.
What we consciously experience, that is perceive, as opposed to the sense organs receive, is very much influenced by what we call top-down cognitive processes. Our expectations, for example, can affect how we perceive a stimulus, and thus many illusions can be manufactured by leading people to expect one thing or another. We actually see something different depending on what we expect to see.
I started to think about how can we dissociate perception from what I call sensation by manipulating the context. Let me explain. So there's a patch of light, falls on my retina. Say it's a colored patch of light that's on my retina. And I say it looks red. So my percept is of red light. Now, I can then vary the color of the light that surrounds that one patch of light. Now, the question is, what is the sensation that's elicited by the central light? Well, I just told you it was red. But if I vary the color of the surrounding light, I vary the way that central color is perceived. So there we have a dissociation between sensation and perception.
Our ability to explain perception in neuroscientific terms is, in my opinion, close to nil at this point. What we can do and what we can hope to do in the near future is to have a very good idea of what the neural correlates of perception are. That is, when you perceive red, there always is a certain subset of neurons in certain subsets of areas in the brain that tend to fire in a particular way. This is descriptive, this is complicated to get at, but it's doable, and I'm absolutely persuaded that we'll get at that point pretty soon. Nobody has a clear idea how to go beyond it, how to explain the fact that that coactivity of these subsets of neurons actually leads to the perception of red, or the sensation, the perception of the smell of almonds. What's happening there? That is something that I think is beyond us at this point.
Perception occurs moment by moment, one perception vanishing as another appears. Each second, our senses take in an estimated 11 million bits of information. But only about 40 of these bits are consciously processed. What is and what is not held onto is often a matter of what grabs our attention.
Visual attention is a filter through which all the stuff that's out there in the world is coming, so that we can focus and attend to one thing at a time. It's typically something that has behavioral importance to us. There are things in the world that sort of demand our attention, a bright light, a loud noise, and then there are things that in our world that we attend to because we seek out things that are of behavioral significance to us.
Our past experience, our biological configuration that day, things that activate certain parts of the brain, to very new things that capture our attention. So on a very generic basis, those and other things are what reach out and get our attention.
People, I need your attention.
This is an everyday word that we use in different contexts, and it shifts its meaning. When we try to understand the science that underlies it, we need to probably differentiate different forms of selective control. The one that I've studied has mainly been the selective one. How do we cope with the overload of information that's coming to our senses all the time? Donald Broadbent, way back in the 50s, suggested that when we're attending to one stream of information, the others get completely excluded, so there's some kind of filter that blocks them from any further analysis.
So one of the more interesting findings related to this phenomenon, which we call inattentional blindness, the idea is because you're focusing attention on something, you fail to notice something else. You're inattentionally blind to it. Your attention is devoted to something else. And without attention, you simply don't consciously see things. In what has become a very influential study by Richard Haynes in the 1980s, he looked at commercial airline pilots in a high-fidelity flight simulator. So in his study, he'd have these commercial airline pilots, very experienced pilots, coming in for a landing in somewhat foggy conditions using this head-up display. And as they're coming in for a landing, unexpectedly there's another plane on the runway. Right? And several of the pilots landed right through it, never seeing it at all. You might think, okay, a jet sitting on the runway, that just doesn't happen. But in reality, the most common airline accidents are runway incursions. And the interesting thing about them is they're almost universally attributable to human error of some sort.
Anne Treisman's research suggests that even though attention is focused elsewhere, in certain circumstances, some information does filter through.
Instead of a total block, what we might have is just a reduction of the information that's coming in from unattended channels, so that you're mainly processing what's in the attended stream of information. But if anything really important happens on another channel, you can still pick it up. And the obvious example is you're talking to somebody at a cocktail party and suddenly your own name comes through from someone speaking behind you, and you hear that when you haven't been hearing any of the other content.
Each neuron or each population of neurons does a particular job of selecting something about what it receives and essentially throwing out lots of things. And that information, or what we call information, for lack of a better word, is then sent to other neurons that do yet something else with it, that eventually send it to yet another set of neurons that do something else with it. And it goes on until either behavior occurs, which we can objectively monitor, and or a perception which we as human beings can experience. But who's reading this? For a very long time, people thought that there was a homunculus inside our heads that was doing the decoding in some sense, and nearly all agree that there's no homunculus in our brains. But we don't really know who does the final reading or the final translation to what we experience as perception.
From a cognitive point of view, the question that intrigued Daniel Simons and his colleagues is what factors influence whether or not something is perceived.
So a lot of what we've done is tried to look at what sorts of things you become aware of in the world, whether they're unexpected or expected, whether they're particularly distinctive or not, whether those are things that you become aware of as opposed to just process in some way more efficiently.
Many of the experiments they conducted relate to what has been termed change blindness.
So we might film a conversation between two people and change their appearance slightly or change some of their clothing from one shot to the next in the scene. And the question was, would people notice these editing mistakes in the movies? Our intuition was that most people are pretty convinced that they would notice these sorts of changes. And in reality, most people almost never notice any of these changes.
Well, the police recommend that we put these signs up around the neighborhood. Anybody who isn't from the neighborhood knows that there's people watching out for each other.
Does it really work?
Well,
We make sense of the meaning of the scene. We pay attention to the things that matter. If it's a conversation, we pay attention to the speakers. If it's an action sequence, we pay attention to the action. And we don't necessarily pay attention to the other details or keep track of them from one moment to the next, because they're just not necessary. If you ask people, how likely would you be to notice this change? 90% of people say, oh yeah, I'd notice that. Nobody does. So it's a 90% overconfidence in how well you would notice these changes in scenes.
It has become obvious to researchers that attention and perception are intimately linked, as evidenced by one study on a basketball court, in which observers focused their attention so intently on one aspect of the game that they failed to notice a rather surprising intruder.
In this study, we would give people a task of, say, counting how many passes the players wearing white made, and they'd have to keep track of the total for a minute. Right. And after about 40 seconds or so, we'd have some unexpected event happen. A person carrying an umbrella, a woman carrying an umbrella would walk through the middle of the display, or in the more striking version of it, a person wearing a gorilla suit would walk into the middle of the display, turn and face the camera, thump its chest, and continue walking off the other side. And these objects, these people, were visible for anywhere from 5 seconds to 9 seconds, depending on the condition. In the case with the gorilla thumping its chest, we found that fully 50% of the people who viewed it and were counting the passes made by the players wearing white didn't notice anything at all unexpected or out of the ordinary. In fact, we're typically really shocked when we told them what they'd missed. And that's what's so striking about this. Not just that we miss these things, which is striking in and of itself, but that our intuitions about what we'll miss are so inaccurate, they're so wrong. And this sort of finding has potential practical significance. One of the most common things you see on automobile accident reports is, I looked right there and just didn't see them. They came out of nowhere. Well, that may well be this sort of phenomenon. You may direct your eyes at something. You may be looking down the street, just as you're looking at this display with these people walking around, and you may be looking right at the person wearing the gorilla suit. But simply directing your gaze someplace doesn't guarantee perception. This doesn't guarantee that you're going to process this at any level of meaning.
Perception is not just opening a shutter and letting a picture print itself on the brain. We constantly filter sensory information and work to organize perceptions in ways that make sense to us. One task that's critical is to distinguish between an object and its surroundings, between the figure and the ground. For example, what do you see when you look at this picture? Just a series of dots, or something more?
You tell somebody what it is, and all of a sudden they see it. We tend to call this perceptual learning, things that are sort of incremental in the changes. It used to be the case that there were these people that would sit on assembly lines, and people have to determine whether the resistors and transistors and so forth are in the right place on the printed circuit board that's been built by some machine or some person down the line. And you look at these printed circuit boards all day long, and you get really good at discriminating and identifying these resistors and transistors and making sure they're in the same location. You've altered the visual system somehow.
If you look at a visual scene, you can always separate an object of interest from its background. So my face from whatever is behind me. In hearing, segmentation takes the form of separating a particular person's speech from the background noise or the conversation of other people.
Okay, sure. Hello? Anybody in there?
What?
Jenny, you haven't been listening to anything I said these last 15 minutes.
Sure I have.
So this ability to pull out a set of interesting stimuli from a background is what we call segmentation. In the case of olfaction, segmentation could be thought of as the ability to identify a chemical component within a mixture. So a typical odor in nature, the smell of flour, the smell of ground coffee, is typically made of many tens, sometimes many hundreds of different molecules. But if you smell the smell of coffee, you don't smell all the chemical components of it. You smell it as a unitary percept, coffee.
Often, it's the overall pattern of inputs, the gestalt, that's important, not the individual elements.
For example, you don't want to see every leaf on a tree normally. You just want to see that there are leaves and get their general properties, like how big are they, how green are they, how much are they moving in the wind. What we're finding is that people have these different modes of attention when we may switch between them. So open the aperture of attention wide, and then you get one set of properties like maybe the general gist of a scene, the statistical properties of whole sets of objects in it, cars in a parking lot, the birds in a flock, and so on. Then when you want to individuate particular elements, like one particular bird in the flock, then you're going to have to focus down, narrow down, and then you will get all the properties bound together in the correct combinations and relations.
Some studies have shown cultural differences in the information that is extracted from a scene.
Taka Masuda and Dick Nisbet have conducted very ingenious series of experiments where subjects are shown a scene where central object is surrounded by many objects. For example, big fish is swimming underwater, and there are many other things behind, bubbles or some stones or some, clams and so on. And simply, the researchers ask subject to tell the story about what's going on in the scene, and Japanese respondents begin the story by referring to the background. Oh, here's some current which is rapid, and there are some stones and some, seaweeds in the back and so on. Now, a big fish is swimming in that scene. But Americans did just the opposite, just beginning the story by focusing on this focal fish. What this fish might be like and what features this fish seem to have, color, size, and many different patterns on the body.
To bring order and form to basic sensations, to the fish images in this scene, our minds follow certain rules for grouping stimuli together, by proximity, by similarity, and by continuity. Even young children show an awareness of these rules of form.
There's a number of particular expectations that babies have been shown to have, that objects are solid material entities that take up space. Two objects won't just magically pass through each other, they'll bonk into each other, or one object can't just pass through a wall. If they see me pull out of my pocket over here a little red ball and tuck it back, and then pull out of a pocket here a little red ball and tuck it back, they make the assumption, well, there's two red balls. They only saw one ball at a time, but they know this little red ball here can't just magically blip over to this pocket, for example. So they're using these expectations to make assumptions about the world around them.
Even when we can't see an object in its entirety, our need for closure pushes us to fill in gaps, to create an image that is complete and whole.
I look around the world here, I know that that can right there continues behind this desk. I can complete it, even though it's not explicitly represented, it's not there in my retina. A lot of this contextual processing is about filling in missing information.
The human mind has a great propensity to bring order out of chaos. And so if we see a partial image, we'll fill in the holes in order to create a whole.
The ability to see objects in 3 dimensions, even though the images that strike the retina are 2-dimensional, allows us to judge distance, another important aspect of perceptual organization. Because our eyes are a short distance apart, our retinas receive slightly different images of the world.
They're what we call binocular depth cues. That is, the image cast in the 2 eyes is different, and that provides, because you're looking at the world from 2 different points of view, and that provides information about the relative depths of these different surfaces.
Under ordinary conditions, our brains merge these different inputs into a single 3-dimensional image. But what happens if the disparity is too great? If the 2 eyes see entirely different images?
One of these experiments is called
binocular rivalry. So binocular, two eyes, and rivalry like, two football teams are in rivalry. So I show you one image in one eye and a different image in the other eye. Let's say I show you an image with a beam splitter. I put an image of the glass into the right eye and this image of this brain to my left eye. Now if I do it correctly, what you might imagine, what you'd see, if I ask you to see, you might imagine, well, I'm going to see a glass and a brain. But that's not what you see. Is let's see, you will only see the glass for 3 or 4 or 5 seconds. Then there's going to be some transition period, and then you'll only see the brain. And then sometime later you'll flip back to the glass, and then you flip to the brain. It's a never-ending dance. You have these two elements that go in and out of consciousness. In your head, there's this quiet competition raging among your neurons. So here you have another case where physically nothing changes outside, and what changes in the inside of your head.
Monocular cues allow us to judge distance and depth, whether we are viewing with one eye or two. For example, the image size of an object appears larger when it's close and smaller when it's far away. Parallel lines seem to come together as they move into the distance. An object that is nearer sometimes blocks portions of an item that is further away. With increasing distance, coarse textures and sharp images evolve into finer textures that are blurred and soft-looking. Imagine what it would be like to see the world in all its color, form, and depth, but not be able to detect motion. How would that change your life?
There are two patients over the last 100 years that are quite famous because it's extremely rare, fortunately, because it's a very debilitating pathology. These people, they don't see motion anymore. They don't see moving things anymore. It's a little bit like being in a disco, when you have strobe light and you see people sort of dancing like this. If you see a car, the car is far away, the car is close by, but they don't see a smooth transition anymore. When you pour water, the water is here and suddenly it's down in the glass. They don't see the smooth transition anymore.
Your brain computes motion based partly on its assumption that objects whose image on the retina is diminishing are moving away from you, and objects whose image becomes larger are approaching. But even that assumption is subject to error when the object is unfamiliar or when few distance cues are available.
How we perceive the world is a combination of what's ready to go in our head and what's really happening out there. It's a combination of the two. So if we have expectancies, we'll assume that what we expected really happened. Somebody else without that expectancy might not see that as happening.
That's surprising, really.
Oh, there's Chuck! Chuck!
The fact that we can glance at someone coming toward us and recognize them instantly as a friend, regardless of angle, distance, or light conditions, is a remarkable human capacity known as perceptual constancy.
Insects, for example, they don't have to learn a lot of new stuff. An insect has a short lifetime and it wants to be able to get to the food and mate and so forth, build a nest. And so it's going to want to have a visual system that knows how the world is constructed and use only that. But we have greater potential for flexibility. We have a longer period of time in which to express ourselves and do more interesting things. And so this flexibility, it enables us to take a piece of information that's gathered through our perceptual experience and use that information for interpreting the world next time we see it.
Together with my husband, Daniel Kahneman, we proposed that we probably need in our theories to distinguish representations that encode the present state of an object in its current location from the long-term stored memory of what, say, a dog looks like. So we want to have a separate representation that tells us, there's this particular dog here with these floppy ears, and the information that we've stored, which we can compare with this particular instance and say, yes, those match closely enough.
A persistent question that researchers continue to probe is how the brain merges all these various inputs into a coherent whole.
So how is it that I can take information from seeing in different aspects of seeing. There's motion, there's color, and there's depth, and there's texture, and then hearing, right? Your voice enters through my ears, but I don't hear your voice here, I actually hear it out there. And, you know, I mean, I can touch you and I can feel you. And so how do I combine all that information? This is a problem, it's a mystery, and it's even more mysterious because if I look at it in the brain, those parts, different parts of the brain analyze different sensory modalities. So one part of the brain analyzes, let's say, faces. Another part of the brain is specifically responsible for analyzing colors. Another part of the brain is responsible for analyzing sounds. So you have different parts of the brain that are engaged in different function, yet the way I experience it is as a unitary whole. And so this is known as the binding problem. How does the brain combine very rapidly? How do 100 billion neurons combine very rapidly information across different domains and present them to me so I see them as one?
I'm going to be probably a couple hours late.
When you're overloaded, well, one of the things is, according to me anyways, that you make binding errors. You know, you don't put things together correctly. You know, you'll simply have more information reaching the analyzing systems in the brain than you can cope with at once. So you'll get two conversations mixed up with each other, for example. You won't be able to read the right sequence of words because others will try to pop in. So I was curious, if we do have these separate analyzing systems, how do we coordinate, integrate them together again and make a unitary object that we can interact with, respond to? So my suggestion was that we'll move attention to one object after another and deal with one at a time, rather than taking them in more globally and running the risk of making what I've called illusory conjunctions.
Toward the end of his career, Nobel laureate Francis Crick also became intrigued by this question.
Crick and I postulated that, well, this is how the brain solved the binding problem, that all the different neurons that are spread throughout the brain that respond to your face, that respond to your voice, that respond to the color, the hue of your face, that, you know, respond that I know something about who you are, etc., they all fire, but they all fire in the synchronized, rhythmic manner. The right experiment to test this are very, very difficult to do. You have to do it in a awake animal or in a awake person. It's very difficult to do these sorts of experiments, so we still don't know whether this hypothesis is actually true or not.
I truly believe that we are at a very, very early stage. I mean, we know lots of things, we can describe lots of things, but if you look at a field that's very highly developed in neuroscience, which is the visual neuroscience, just the mechanistic understanding of the way in which you build a neuron that can recognize a face, independent of color, contrast, size, orientation, is something that we really can't explain. We can't do that in mechanistic terms. So if we can't even do this, how can we explain the more mysterious aspects of perception that we can't even describe in an objective manner?
Inside Out is a 22-part series about psychology. For information on this program and accompanying materials, call 1-800-576-2988 or visit us online.